In today's video, we're going to be doing an introduction to the OSPF protocol. I'm Richard Reyes, CEO of NLink IT. Let's get started. In previous videos, we showed how to build a network using static routes, and we were able to establish communication between the three LAN networks PC1, PC2, and PC3. Right now, we have the same configuration as in the previous video. We haven't made any changes. Notice that PC1 responds to the ping command to PC2. It also responds to the ping command to PC3. And Google's DNS responds correctly. In other words, we have internet access. Notice that PC2 also responds to the ping command to PC1, PC3, and Google's DNS. Similarly, from PC3 we have communication with PC1, PC2, and Google's DNS. So far everything's going well, but what would happen if the link between R3 and R1 fails? The answer to that question is that R3's LAN network would become isolated and cut off. The same thing would happen if the link between R2 and R1 fails. R2's LAN network would lose communication with PC1 and PC3. So, to resolve this situation, we need to establish a link between R2 and R3. Which will make our network a redundant communication system with the goal of guaranteeing availability and reliability in our network infrastructure. This whole system will work in a coordinated manner. We can establish this new link on any free port on R2 and R3. In this case, we'll use Ether2. The network we'll use will be 172.168.2.0/30. Let's write these new IP addresses in the boxes that correspond to each router. And now we'll move on to configuring these new IP addresses. So we'll go into R2 and get started. Now we'll go into R3 and do the same thing, configure the IP address. We've now configured the new IP addresses on the new link, but that's not enough to establish redundancy since we still need to configure the OSPF dynamic routing protocol. This protocol utilizes specialized algorithms and enhances network performance. Why? OSPF is highly comprehensive and offers multiple configuration options, but today I want to walk you through the basic setup and the benefits it provides. Remember that right now the network is operational because of the static routes we configured in previous videos. But it's best to disable them since the OSPF protocol will take over this routing work. So let's start by disabling the routes on R1. Now we'll go to R2. And we'll also disable the routes on R3. Now we'll go to PC3. Notice that we've already lost connectivity between the different LAN networks. And we've also lost internet access. Let's check on PC2. And the same thing is happening here. There's no connectivity. Now we'll go to PC1. We can see that PC2 and PC3 aren't responding. But the DNS is responding because the link to the internet is operational. But what happened here is that communication between the different routers was broken due to the elimination of the static routes. But we're going to restore all of this in a more efficient way, and with the main added benefit of the redundancy that OSPF offers us. So let's get practical with the basic OSPF configuration. We'll go into R1, go to Routing, OSPF. Then we go to Instances, click the plus sign. In the originate default option, we select Always. After that, we go to Areas, click the plus sign, then in the Name option, we make sure that it's OSPF Area 0. And click OK. Finally, we go to Interface Templates, click the plus sign. In the Interfaces option, we add Ether2 to R2. Click OK. And repeat the process for the interface Ether3 to R3. Click OK. And finally, we add the interface Ether5 to PC1. And select the checkbox Passive, since this Ether5 interface is the LAN network interface. Click OK. Now we're going to repeat the process on R2 and also on R3. With these simple steps, we finished the basic OSPF configuration on R1, R2, and R3. Now let's see the results on PC1. We've already restored communication with PC2 and also with PC3 and the internet. We'll go into PC2. And here we can see communication restored with PC1, PC3, and the internet. And finally, we'll go into PC3. And here we can see that we have connection with PC1, PC2, and the internet. All of this is being done through the OSPF protocol. This happened in part because the routers were able to establish adjacencies with each other, as we can see on the screen. R1 has this neighbor, which is R3. And it also has R2 as a neighbor, according to our IP address diagrams. Let's go into R2 in the OSPF window in the Neighbors tab. We can see the adjacency that R2 has established with R3 and with R1. And finally, when we go into R3 in the OSPF window in the Neighbors tab, we can see the adjacency with R2 and with R1. So we've reached the key moment, which is to do the redundancy tests, which is the main reason why we've configured the OSPF protocol. For this, we're going to go into PC3. And using the traceroute command, we can see the hops that the packets are following to reach PC1. Here we can see that the second hop is the IP address 172.168.3.1. If we go to our topology, we can see here that this IP address 172.168.3.1 belongs to Ether 3 of router R1, meaning that the packet is traveling from PC3, passing through router R3, traveling through this link, entering through Ether 3 of router R1, and then continuing its journey through Ether 5 until it reaches PC1. Now we'll go into router 3, go to IP routes, and we find this route here that was created dynamically by the OSPF protocol, telling the router to reach PC1 subnet 192.168.1.0 through the gateway 172.168.3.1. In other words, R3 reaches PC1 through Ether 3 of R1, which is where this link is connected. But what would happen if this link were to fail? What would happen is that R3 would automatically, through OSPF, enable a new route to be able to reach PC1, this time through router 2 or R2. In other words, this means that the service is always available. This is commonly called redundancy. Now we're going to go into router R3 to analyze live what will happen when the link from R3 to R1 fails. To simulate this break, we'll go to IP addresses and disable the IP address of the interface that connects to R1. And notice that regardless, the algorithm that OSPF uses has calculated, created, and enabled a new route to reach PC1. That new route is the route right here. This route has managed to establish that connection. Now, through the gateway 172.168.2.1. Going into PC3, we find that only one packet was lost while the algorithm made a change in the route, which is excellent. If I repeat the traceroute command to PC1 again, we find that 4 hops are now required, and hop number 2 is the WAN network of R2, that is 172.168.2.1, and hop number 3 is 172.168.1.1, that is R1. Let's go to the topology, and I'd like to explain this more graphically. Since this R3 to R1 link is out of service, it's broken for some reason. R3 now uses this link to R2 to communicate PC3 with PC1, and in this way provide redundancy to the solution. Again, let's go to PC3, and you can see the ping working fine. Now let's go back to R3, and we'll activate the IP address again to restore the original connection. And here we can see that OSPF immediately recognizes its neighbor 172.168.3.1 and enables the route to PC1 again through its original gateway 172.168.3.1. If we go into PC3 again, we observe that there's no packet loss to PC1, which demonstrates the efficiency of OSPF. Very good. Again, in the network topology, we can conclude in the same way that R3 calculated a new route when its main link with R1 failed in order to keep communication active. The rest of the routers on the network assume this same behavior under the same circumstances. For example, if PC2 has communication with PC1, and this link between R2 and R1 fails, then R2 will automatically send the traffic through its R2 to R3 link. Okay friends, in this way, you can take your networks to another level, to a professional level, with a high level of service availability. Remember that this was just an introduction to OSPF and a basic configuration. Of course, many more things can be adjusted in order to increase the level of service availability, but for the moment, this has been the scope of this video. I'll see you in the next lab. Remember to like this video and share it.